In this video, we are going to go through the steps of glycolysis. The idea is that if we understand what steps happen, then we'll be well positioned in future videos to start asking why do they happen and how do we get energy out of glycolysis. So quick orientation, we are talking about the glucose transit network. So here I've got a map of central carbon metabolism. And right now we're focusing here on this region, which are basically molecules that are interconvertible with glucose. I talked about this in terms of a transit map analogy. So what we're going to be looking at today is the main transit line down the trunk, the central trunk, that is glycolysis. These different lines, these different metabolic pathways have different functional and metabolic roles. Specifically, glycolysis is going to convert glucose to pyruvate in an effort or as part of a process to extract energy. So that's the thing we're talking about here. We're starting at glucose here at the top. We're ending up at pyruvate in the bottom. And what we'll see is we're going to spit out some ATP molecules along the way. So the overall reaction for glycolysis is as follows. A glucose molecule comes in with an ADP, 2 inorganic phosphates, and an NAD+. After the entire process of glycolysis, we end up with 2 pyruvates. We end up with, I'm in the way. I should disappear. There we go. I disappeared. 2 pyruvates, 2 ATPs, 2 NADHs, as well as some spare parts that came out the other side. Instead of this happening in one giant reaction, like basically every metabolic pathway, we're going to break this one giant reaction into multiple steps. In this case, there are 10 steps. I'm drawing this as a process diagram, which I'll be using throughout this. So if you haven't seen my video on process diagrams and you're confused, you should go check that out. But basically, I'm going to show this at a very high level, and then we're going to talk through each reaction one by one. But we've got a glucose going to a glucose 6-phosphate, a glucose 6-phosphate going to a fructose 6-phosphate, a fructose 1,6-bisphosphate. All of these are 6 carbon molecules. We're then going to break that 6 carbon molecule into 2 3-carbon molecules. So this is a 3-carbon molecule, dihydroxyacetone phosphate, and another 3-carbon molecule, glyceraldehyde 3-phosphate. At this point, the pathway has doubled because we've taken 6 carbon units and we've made them into 3. And then we're going to undergo a process where those 3 carbon units all go through glyceraldehyde 3-phosphate, go to 1,3-bisphosphoglycerate, 3-phosphoglycerate, 2-phosphoglycerate, phosphoenolpyruvate, and pyruvate. Now, if you're taking a class from me, I would say at this point, hey, don't memorize all this stuff. You'll always be able to look it up, and I think that's really true. We're going to be going, so even if you're not taking a class from me, maybe don't memorize it. I don't know if your instructor says memorize it. But we're going to go through it at sort of differing levels of detail over a set of videos to learn how it works. And hopefully you'll gain familiarity as we go through it and understand how it works. But right now, we're just going to go through and try to understand what are the chemical transformations that are actually occurring in glycolysis. So we're just going to go through each step and say what happens to these as molecules so we can understand, say, how ATP gets made at the end of the day. All right, so step 1 is catalyzed by the enzyme hexokinase. What it does is it takes a glucose, shown down here, it's a 6-carbon sugar. It takes an adenosine triphosphate, an ATP. And what it's going to do is it's going to take the trailing phosphate off of this ATP, and it's going to put it on the 6th position of the glucose. And so you recall that sugars are numbered 1, 2, 3, 4, 5, 6. So this gets the name glucose 6-phosphate because we put a phosphate on the 6th position. The result of this is an ADP. So we lost the phosphate off the end of this. And then our G6P here. And then we have a proton because we basically had to pull a proton off of the hydroxyl to make that new bond. Okay, step 1, cool. Step 2. Step 2, we're going to take our glucose 6-phosphate and we are going to convert it to a fructose 6-phosphate. So this is fructose 6-phosphate. The numbering still refers to the fact that this is on the 6th position of the sugar, but now we're on a fructose molecule. I thought it's actually worth, let's actually go through how this works even in the enzyme. So recall that sugars can go between a ring form and an open form. So here I'm just showing glucose. The phosphate is at this position, which I'm just going to draw as a circle here. This can open into a ring form where I've kept the colors correspond to the numbers. So this is the 1 form here, or the 1 position. This is the 6 position. What we've done to form this ring form is we've broken this bond here. That means that our phosphate is down here on the 6th position. This is a glucose, which means this is an aldose sugar because it has an aldehyde at the top. What this enzyme does is it actually makes it into a ketose sugar by moving that carbonyl down 1 carbon. So now it's on the 2 carbon without changing anything else. So basically the phosphate's still on the end. What we've done is we've swapped these 2 molecules, so now the carbonyl, or these atoms, sorry, so now the carbonyl is at the 2 position. And now we are going to reform a ring. And so a glucose prefers this form here, which is a 6-membered ring, or a purinose form. A fructose prefers a 5-membered ring, which is called a, I just lost it. Furanose. There we go. Wow. Furanose. That was almost a total failure. Furanose form. So the furanose form, what we're seeing here now is we're forming the ring. We're forming a new bond here between this oxygen and this carbon to form the ring. And that puts us into a different geometry, right? And so the way that enzymes work from here on out is I can tell the difference between a glucose, which is a 6-membered ring, and a fructose, which is this 5-membered ring with the 2, 1, and 6 carbons hanging off the outside. Okay, so that's the transformation that's happening here. We still have the phosphate at this position, at position 6. We've just changed whether we're, basically you can think about it as we've gone from a 6-membered ring to a 5-membered ring by changing between a aldose sugar and a ketose sugar. All right, so we've got our fructose 6-phosphate here. What do we do next? The next step is to take an ATP, 1 more ATP molecule, and what we're going to do is we're going to take the phosphate off of the ATP and we're going to stick it onto the 1 sugar position. So this is the 6 sugar, this is the 1 sugar. We're going to put the phosphate onto that. And what that yields is this molecule here, fructose 1,6-bis phosphate. And an ADP. We've lost the ATP there. Now, if you've been keeping track at home, we've invested 2 ATPs thus far into our glucose. So from here on out, we're actually going to start gaining energy back. We're going to start making ATPs. To this point, we've consumed ATPs. Okay, step 4. We have our fructose 1,6-bis phosphate. We're going to break it in half. We're going to break it into dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. These molecules are shown here in the same orientation as the graphic. So this is, come on, pen, there we go. Dihydroxyacetone phosphate, glyceraldehyde 3-phosphate here. To help us keep track of what's going on, actually, I should say which bond we're cutting. We're cutting this bond here in the sugar, and actually this bond. We can think about this, and actually the way this enzyme does this is it does this with a ring opening event. So it opens up the ring, and then it cleaves between the 1, 2, 3 carbon and the 4, 5, 6 carbon. So if we numbered these, what we would get is actually that this will start at this one because it's easier to see because it's more direct. This is 4, 5, 6, and this is actually 1, 2, 3. We flipped it over. And the reason that we did that is because once we start drawing molecules later, we're going to put the phosphates on the bottom. Dihydroxyacetone phosphate is actually symmetrical about this ketone group, except for where we put the phosphate. So we can actually number this however we want. This could be a 1, this could be a 3. So we end up sort of flipping this over. So this dihydroxyacetone phosphate has its phosphate as I'm drawing it here on the end. Wow, that probably made no sense. Let's just say it this way. We cut it in half. We have the phosphate here and the phosphate here. This molecule, because there's basically no chirality in the system, it's symmetrical about that, we can just redeclare. Now, this is 3, this is 2, this is 1, just to make our numbering consistent with down below. The phosphate's always on the 3 position. Okay. Key thing, we chopped our fructose 1,6-bis phosphate in half, and we made dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. The next step actually involves only the dihydroxyacetone phosphate. We're going to convert that into glyceraldehyde 3-phosphate. It's just an isomerization reaction. There's no change in the number of atoms involved. We're just rearranging them. We're basically taking this keto and we're putting it into an aldose type sugar. And in fact, it's easiest to sort of mentally combine steps 4 and 5 because what we've done is we've taken our fructose 1,6-bisphosphate and we make it into 2 G3Ps. So we've chopped glyceraldehyde 3-phosphate into 2 pieces that are both G3Ps. Sorry, we've chopped fructose 1,6-bisphosphate into 2 pieces, 2 glucose 3-phosphates. Okay, so what this means is stoichiometrically all subsequent steps 6 through 10 are doubled. And that's because each of the G3Ps, and we made 2 of them, is going to turn into pyruvates, which means that we're going to generate 2 ATPs per G3P. That means we're going to generate 4 total. So each of these is going to spit out 2 ATPs. And since this whole thing, there's 2 of them, that means we're going to get 4 ATPs out. All right, soldier onward here. What's our next step? So our next step is to take glyceraldehyde 3-phosphate here and do a bunch of stuff to it. This is one of the major, most important steps in glycolysis. We're going to spend half of a whole video, not this one, on this specific reaction. So right now I'm just going to outline what happens so that we can talk about what it does later. So what happens is in this reaction is we're going to take our glyceraldehyde 3-phosphate here, an inorganic phosphate here, and an NAD plus molecule, which I am showing here as a full structure. I put it as this full structure. It's so we can see the whole thing. But if you will saw my thing on currencies, you'll remember that basically all of this here is a handle that the cell uses to recognize NAD plus and NADH. And that this region here is the business end that's going to do the redox chemistry. So I'm just going to call that all R. So R is now gone. And from here on out, I'm going to draw this as an NAD+, right? It has the functional group that is going to be able to take the hydride ion, or the hydride, sorry, to be pick up electrons. Okay, so we have our glucose 3-phosphate. We have our inorganic phosphate. We have our NAD+. This enzyme catalyzes the reaction that is going to take this phosphate. Actually, we'll not start at the phosphate. We'll start here. It's going to take the hydride off of the glyceraldehyde 3-phosphate, and it's going to stick it onto the ring of the NAD+. And it's going to then glue the phosphate in where that extraction happened. So we end up with this molecule here, which is 1,3-bis phosphoglycerate, and we have our two electrons at our proton that get pulled off this hydride that now put us into NADH. So we went from NAD plus up here to NADH here, and that reaction is coupled to this phosphotransfer. We're taking a phosphate out of the environment and we're sticking it onto our glyceraldehyde 3-phosphate to make 1,3-bis phosphoglycerate. Whew. English. Okay, great. That's step 6. If you have been keeping track, there's 10, so we're actually getting really close to being done. So the next step here is we're going to take our glyceraldehyde, our 1,3-bis phosphoglycerate, and we're going to run it in this direction. This is actually a reversible reaction, but this direction is going to form this 3PG, 3PG. It's going to couple that to phosphotransfer. So here, I'm drawing an ADP. And what we're going to see is this phosphate is going to come off and get glued onto the end of the ADP, making an ATP. The resulting molecule that's left over on the carbon side is we go to this thing 3-phosphoglycerate, or 3PG. And you'll notice that we've replaced this phosphate here with just a carboxylic acid or carboxylate form here. Okay. That's step 7. Let's go through 8. 8 is we're just going to do a very simple rearrangement. So we're going from 3-phosphoglycerate, meaning the phosphate is sitting on the 3 carbon right here, to 2-phosphoglycerate, meaning it is now sitting on the 2 carbon. So we just moved that phosphate over. We swapped the phosphate and the hydroxyl. Step 9, we're going to form a molecule called phosphoenopyruvate. And basically what we're going to do is we're going to pull a water off with a proton. And what that's going to yield for us is this enol here, phosphoenopyruvate. This is not a particularly stable form. This is populated relatively transiently. But what that means is we can take this transiently populated phospholinopyruvate. We can grab a proton from the environment and an ADP molecule, and we're going to transfer the phosphate onto the ATP. And ultimately, what that yields for us is an ATP and a pyruvate. So we've managed to make 2 ATP molecules over the course of this second arm of the reaction, or the last part of it. So here's the overall reaction again. We have glucose coming in with 2 ADPs, 2 inorganic phosphates, and 2 NAD pluses. We could actually expand this out if we wanted to make this actually plus 2 ATPs going in. Our final output of the reaction is going to be 2 NADHs, 2 ATPs, and 2 H2Os. But in reality, this is 4 ATPs, right? We spit out 4 ATPs over the course of the reaction. We invested 2 ATPs at the beginning, and so you subtract those out. Basically, where this 4 comes from is 2 in, 4 out, therefore 2 ATPs. So the overall reaction is going to give us glucose and going to 2 pyruvates, in the process reducing 2 NAD pluses to 2 NADHs and making a total of 2 ATPs coming out. All right. And what glycolysis consists of is taking this and breaking this into this, multiple different steps. So we have these 10 different steps. What we're going to do in the next couple of videos is unpack what happens at some of the key steps in here, as well as look at the different regulatory schemes that are applied to this. But now hopefully you have at least the architecture. This is the skeleton outline of the steps that are happening in glycolysis. So now we can understand what happens across each of those steps. So thanks for your time, and I will see you later.